Hello, and welcome to the Data Science Institute's virtual seminar series. My name is Dr. Leno da Silva, and I'm a data science ambassador at the Lawrence Livermore National Laboratory. Data science is essential to many of the lab's key program areas. With the help of some of the world's most advanced supercomputers, we work in a variety of fields and application domains. Through basic and applied research, our data scientists are working to solve some of the world's most pressing challenges, in areas ranging from precision medicine and advanced manufacturing to energy and national security. Here at the lab, the Data Science Institute acts as a hub for data science activities, including this seminar series and other events to introduce new ideas and encourage collaboration. Speakers from other institutions are invited to share their innovative approaches with our data science community. With recordings of these seminars, like the one you are about to watch, we are reaching a wider audience than ever before. So, welcome. If you have questions or want to follow up after the presentation, check us out online at data-science.llnl.gov or send us an email at dsi-seminars@llnl.gov. Now, sit back, relax, and enjoy the seminar.
We'd like to welcome Chad Schaefer, professor of statistics at Carnegie Mellon University, who works on an area near and dear to my heart, the statistical methods for high-dimensional data and complex systems. And in particular, we'll be talking about applications to another area I find particularly fascinating, next-generation surveys of deep space from the Rubin Observatory. Take it away. Thank you.
Thank you. Thanks a lot, Min, and thank you all for being here. And I really want to thank the lab for giving me this opportunity to visit, and especially to Michael, who spearheaded this opportunity for me to be here. So I'm going to be talking about astrostatistics in the era of the Rubin Observatory. Maybe you saw last week, or a couple weeks ago now, maybe you saw the big news a couple weeks ago. We actually had an event here at the lab where the first images from the Rubin Observatory were released to the public. A huge step forward for our understanding of the universe. So I'm going to talk here about, just a series of examples and different contexts in which statistics plays an important role in the analysis of this sort of data. Here's another image that came out of that event. This is the Trifid Nebula and Lagoon Nebula. As you can see, it's zooming out. It's trying to, at least. You can see the scale of the image there. That's the moon as we see it. So the moon's about a ½ degree on the sky. Each of these images is about 10 square degrees. This is one image as taken by Rubin. So you imagine this telescope will be taking 1,000 of these images on average each night for 10 years. It's pretty remarkable. So I just want to go through some quick facts regarding the observatory. So I saw on their website, I didn't know this, but it was first conceived in 1996, that's what they claim, and the construction started in 2015. I've been involved since before then, so it's been quite a while. I've been hearing about this project. This survey is starting now, essentially. It's located on Cerro Pachón in Chile. It's going to be a 10-year survey conducted of the southern hemisphere. The camera is the largest ever constructed, 3,200 megapixel, weighs 6,000 pounds. So as I said, it'll be 1,000 images on average per night, 20 terabytes of data each evening. And also each evening, and this is one of the critical innovations of Rubin, is that you're going to get alerts on objects that are changing in time. So our understanding of asteroids, supernova, other transient and variable events is going to increase dramatically. In total, they expect about 60 petabytes of raw image data, and 38 billion objects will be observed over the life of this survey. And the goals for something so ambitious are quite varied. Understanding the nature of dark matter and dark energy, creating an inventory of the solar system, so you can see it goes on from the smallest to the largest scale, mapping of the Milky Way, and also exploring how objects change in time, as I mentioned a minute ago. There have been other large surveys, including the Sloan Digital Sky Survey, but one of the main significances of this survey is that you will actually be able to observe how objects are changing in time. All right, so LSST, this Legacy Survey of Space and Time, that's what they call the survey that's going to be conducted on the Rubin Observatory, is really just the latest in a progression of these sky surveys, as we call them. These are large-scale, multi-institutional collaborations. They have multiple diverse scientific objectives. Fortunately for the general scientific public, they have relatively open access to data. Anybody can go and pull down any amount of SDSS data that they're interested in. LSST, or the Rubin Observatory, will have a period of time where it's not publicly available, but it will be available in a couple of years once data starts to be gathered. And the goal often is the production of what we call catalogs of objects of the same type. So a galaxy catalog, a quasar catalog, maybe a star catalog, along with properties of those objects. So I'm a statistician. I like to think of things in statistical terms, of course. I see this as being, a large data set, of course, but it's a sample being taken from a large population of all the objects that are out there. And what we've seen is an evolution over the past 50 years or so of a shift from the study of individual objects out in the sky to what we would call catalog-based studies. So thinking about things in statistical terms, thinking of it as I have a sample observed from this larger population, what can I infer about the universe from that? So that's where I see the role of data science, which I'm using as an overarching term for statistics, machine learning, whatever you want to call it, AI, inferring properties of the universe from this available sample. So a crucial ingredient to this is the so-called cosmological principle. The universe is isotropic. We are not in some special position in the universe. So what we are getting to observe is, as we look in any direction, is just a random sample of the universe. It's isotropic and homogeneous. And another thing I always like to emphasize is this notion of what I call an evolution from variance-dominated to bias-dominated inference challenges. So if you go back 30, 40 years, sample sizes in astronomy were small enough that you could make some pretty rough assumptions regarding the distributions of quantities, and it would be fine. Your problems were mostly associated with variability, with variance. But now at Rubin scales, with that amount of data, any flaws that are present in your assumed model form can be revealed, right? This is a bias problem. So a lot of the methodology and some of the things I'll be talking about today is representing this shift. Starting with, the variance problems, but now today thinking more about bias. How do we deal with the fact that maybe our best understanding of the relationship between cosmological parameters and what we can actually observe comes from a simulation model? How do we do statistical inference in that sort of situation? At the same time, as you get more data, people aren't just interested in estimating parameters to greater precision. They start asking increasingly more complex questions of the data. So as we get more and more data, the sort of questions that people are encountering are just getting more and more complex. So that's another place where data science, developing more sophisticated methods, has been crucial. So just a quick example of this. Quasars, among the furthest observable objects in the universe, these bright active centers of galaxies. You're seeing literally some sort of outflow from matter being sucked into a supermassive black hole. This figure here shows about 13,000 quasars that were observed by the Sloan Digital Sky Survey, which I mentioned a minute ago. This is from their so-called data release 3. Outside of this region, they're truncated. The data are truncated because of contamination, or it's difficult to observe at those distances. So one problem is to estimate the so-called luminosity function, what we would just call a density in statistics, the distribution over this space. So different theories regarding the universe make different predictions for the form of this distribution. Now, if we go back, I just found a random sampling, or maybe not so random sampling, of papers that talked about this problem, looking at the growth of the sample sizes that have been used over the years. SDSS, its 16th data release, had about 750,000 quasars in its data set. Rubin is projected by the end of the 10-year survey to have over 10 million of these. So that gives you a sense of the scale of increase that we're seeing here. So with more quasars, you can start to ask and hopefully answer more sophisticated questions. Like you could start asking, getting more precise estimates of particular conditional distributions, thinking about different subsets of the quasars, and then estimate the parameters, the so-called cosmological parameters that characterize this distribution to greater precision. So that's the sort of evolution that we've seen over these past 30 years or so as we've moved from smaller samples to larger samples. And again, Rubin is just the latest step in that process. Okay, so what I'm going to do here is kind of put, I'm creating a framework here for a class of astrostatistics problem. And I don't want to claim that every single statistical problem in astronomy fits into this framework, but it does capture a lot of what we try to do. And I think it's a useful way of viewing this class of problems. So we're going to talk about the raw observables. I'm going to talk a little bit about parameters of specific objects, how those get summarized into what I call the canonical parameters, and finally the estimation of cosmological parameters. And a lot of the problems that are faced on some level involve the ultimate goal is the estimation of these cosmological parameters. So what I'm going to do is just kind of go through these stages and talk about different problems that arise and different challenges that arise at these different levels. Okay, so let's start by talking about the raw observables. Well, certainly a fundamental observable in astronomy is the amount of flux we're getting at different wavelengths. So if I was able to observe the full emission spectrum of an object, here I'm showing an example of galaxy spectrum as observed by SDSS. If I was able to get this information for all objects, I would be in really good shape. This holds a wealth of information regarding the object. Unfortunately, spectra are relatively difficult to measure. So this image here, you can see a plate from SDSS. What has happened is prior to the drilling of the holes in this plate, they've used the camera to determine where the objects are, and then the holes are drilled in those specific locations. The plate is placed onto the spectrograph, and you can see this individual attaching the wires here for the spectrograph. It's a fairly time-consuming process to gather all of these spectra. So instead, the move has been towards using digital cameras, using CCDs to measure the intensity of the objects, through a handful of filters and bands, through a handful of bands. LSST, Rubin will have 6 different bands that objects will be observed through. This is referred to as photometry. And this little animation here is showing the Rubin camera with the different filters being switched and how the image changes in those different bands. Okay, but if that's what I'm getting, all I'm going to see is a low-resolution version of the spectrum, right? Instead of getting this very fine-grained information from the emission spectrum, I'm only going to see the spectrum as viewed through these handful of bands. And what I'm showing here are the SDSS filters. So, for instance, SDSS gathered spectra for 3 million galaxies. Rubin is projected to give us photometry for about 20 billion galaxies. So, a lot more data, a lot more galaxies observed, but much coarser information. So in addition to that photometry, we of course could talk about how information varies spatially. There's a lot of image data out there of objects. We'll get a lot of image data out of Rubin, of course. Again, observed through different bands. So different studies use image data for classification or measuring different properties of galaxies. Here's an example taken from the so-called CANDLES survey. On top of that, we have also observed how the photometry changes in time. So we might call this time series data in statistics, but in astronomy it's referred to as light curves. So I'm showing how the intensity of this object, here the example is a supernova, how its intensity is changing in time through 5 different bands. All right? So Rubin is projected to image each location about 100 times per year on average, and that's going to generate a massive catalog of transient and variable objects, things that are changing in time, including about 10 million supernovae. Okay? So that's what we get to observe. Photometry, varying in space and time. The challenges become working with this low-dimensional, low-noisy photometric data and still getting the science that we want out of it. So from there, we're going to take this raw data and we're going to talk about summarizing it, estimating specific parameters of the individual objects, so parameters of the galaxies, quasars that have been observed. And again, the challenge is doing these things using only this coarse information. So a first example is just identifying what type of object it is, right? An object must be classified based on its photometry, based on its light curves, maybe based on an image of it. The light curves have irregular spacing. The errors are quite heteroscedastic, we would say in statistics, just meaning the error variances vary across them. A lot of the methods for noisy time series or any time series that have been developed in the field of statistics assume you have regularly spaced observations and make very simple assumptions regarding the error distributions. So these problems in astronomy, this light curve classification in particular, have really pushed the boundaries as to what methods can handle. So here I'm just showing a few light curves taken from the Catalina Sky Survey. And you can again see, so some of them are blazars, some of them are cataclysmic variables, and just a wide range of number of observations, the spacing between the observations, and classification using this sort of data can be very challenging. And it's one of the biggest problems that Rubin is tackling, how to classify using these sorts of light curves. So a question I often ask is, or people often ask is, what representation, you start with this light curve, what representation of it is the most useful for classification? So one simple example is people summarize a light curve using its so-called structure function. So all that's happened here is for every pair of observation within a light curve, you look at the change in time, that goes on the x-axis, and then the change in magnitude, that goes on the y-axis. So you imagine all the possible pairs you could construct, they get placed into this plot. This is referred to as a structure function. And then maybe some simple summary of this function is used as the feature that gets put into the classification algorithm. Some of the simplest early approaches even fit straight lines through these plots and use the intercept and slope of those lines as features. I've seen things also where people have just treated this simply as an image and fed it into a convolutional neural network and tried to classify based off of that. But again, the underlying question is, what representation of that original data is the most useful for classification? Now, one thing that we had been looking at was trying to do this from a more physics-informed perspective. So thinking about if I had actual spectra of these objects, right? If I had CV and blazar spectra, those would be very useful for classification. Again, a very rich source of information. So the question we asked is, what linear combinations of the spectra are both useful for classification, right? If you give me a sample of blazar and CV spectra, I could learn something about what features of those spectra are useful for classification. But on top of that, are well approximated by photometry. So if I could learn what those features are, then I could sort of piggyback off of that and try to use the photometry to predict those features and then use those features for classification. So I think this sort of physics-based thinking about these sorts of problems is crucial, and I think we see more and more of that these days. And this is just an example of one such feature. So this particular feature of the spectrum is both useful for classification and can be approximated well using the photometry, because it is in some sense a linear combination of those passbands, or close to one. So we did something similar in a recent paper where we used similar ideas to try to estimate the intrinsic galaxy size. So in this case, we used this really high-resolution simulation model of the universe, the so-called illustrious TNG simulation model. And same sort of idea. We tried to use, within the simulation world, I've got all the information I need. I know everything about all the galaxies, and I know all of their properties quite well. Of course, I'm trusting that that simulation is representative of the real universe, but that's where I'm relying on, the theoreticians, the people who build these models. But within this work, what we did was we tried to learn the features of the galaxies, which, one, were important for estimating the size of a galaxy, that were strongly related to the size of the galaxy, but were also well approximated by things that I could actually measure in a photometric survey. So the same idea, the idea of finding what representations are the most useful by using the underlying physics. Again, I think these sorts of ideas are going to be really important as we deal with data on this scale. So the simulation model, in some sense, is guiding what features we're looking for. Yeah.
Maybe you'll get to it, but there's can you say anything now about machine learning discovering features versus this kind of constructive feature?
Yeah, there's certainly a lot of.
Can you ask the question again? Oh, sorry, I always forget the mic.
Oh, yeah, no, Michael asked. Oh, sorry. He asked about, tell me if I'm mischaracterizing it, but you asked about, there's a lot of methods out there for feature engineering within machine learning. I don't know, I haven't had great success with those kinds of things. I think that there's still quite active area of research, but I do know that constructing features is the key to almost any classification regression problem. I hear that again and again from people, and it's been my experience as well, that you can have all these fancy methods, but ultimately, if they don't have the good features, they're not going to perform that well. But I haven't seen that those kinds of methods work great in these problems yet. Okay, so another example of an object-specific parameter, I couldn't pass over this one, is the so-called redshift. All objects in the universe are moving away from us. We have the expansion of the universe. This produces a Doppler shift in the observed wavelengths of light relative to when it was emitted. So redshift is just a way of quantifying the amount of shift in the wavelength since it was emitted. A fairly simple idea, but a crucial property of an object. It's a measure of the distance, how far away that object is. But of course, we know that as we're looking further away, we're actually seeing back in time. So it's also a proxy for the time at which that the object was observed. So studying objects at different redshifts is studying the evolution of the universe. So having a good handle on the redshift of different objects becomes crucial. So estimating redshift using a spectrum is easy. You just line it up with a template, you can do a great job. But the so-called photometric redshift estimation problem is very challenging. So if you're interested in this, I encourage you to look it up. There's any number of papers where people are trying to tackle this program. It's one of the biggest challenges facing a survey like Rubin is doing photometric redshift estimation well or adequately. You can imagine a lot of the methods are machine learning based. You build a training set built off of a spectroscopic sample, things like SDSS, where you know the redshifts well, and now you're going to extend it to this photometric survey. But in addition to it just being a very difficult supervised learning problem, you also have a lot of questions about, a lot of challenges surrounding how representative is that training sample with what you're actually going to observe, right? Spectroscopic data tends to be higher quality, closer up data. You're trying to extend that into a wider domain. It becomes quite challenging. So you see a lot of work with like covariate shift, those kinds of things in this space. All right, here's a very recent paper that I encourage you to look up if you're interested, where they were thinking about this using a deep learning approach. I have something written here. So they were taking a quite holistic approach where they're taking the original image data and from that learning something, properties of the objects along, including the redshift, what type of objects they are. I brought this up mainly just to highlight the sophistication with which these problems are being attacked. And on top of that, it's not just going to give to you an estimate of the redshift. It also is returning a error distribution, a posterior, on each of those redshifts, which is crucial in order to carry forward into the downstream analyses. And this is a plot that I pulled out of that paper, their method, the so-called deep disk method, showing the degree of performance. And it gives you, again, a sense of how challenging the problem is, comparing the true versus the estimates and how complex the error distributions are, right? The shape of the error distributions are very irregular, right? And again, comparing with a couple of other methods, and in all three of these cases, you are going to get these conditional distributions out, which are quite complex. Again, and storing all this information, imagine you have billions of these objects observed by Rubin. They all have to be stored and then propagated forward for downstream analyses. And another thing that I've heard talk about is questions of how to store the joint distribution between redshift and other properties of the object. Those joint distributions are certainly not simple, but you want to be able to retain all of that information. Okay, so wrapping up this part, the key point I want to make here is that methods for estimating these properties of astronomical objects must work efficiently and accurately with photometric data. And in addition, attach some quantification of the error to those estimates to be practical. Okay, so we've talked about this issue of estimating object-specific parameters. From there, I like to think of it as the next stage as you're summarizing those parameters into what I call the canonical parameters, the natural parameters. These are statistically natural from an estimation standpoint, but they're not what we're ultimately interested in estimating in a lot of problems. It's like a halfway point, if you will. These could be thought of, the estimates of these parameters could be thought of as crucial summary statistics, taking this massive amount of data and reducing it down to more manageable sizes for the final analyses. Again, using a little statistical jargon, ideally these estimates would be minimally sufficient, we would say. They would have all of the information regarding the ultimate parameters of interest, but not be any larger, right? Not be any higher dimensional than necessary. All right, so I already mentioned one such example, the so-called luminosity function. So this is a summary. When I estimate this distribution over this 2D space, I'm summarizing all these observations of quasars. I'm summarizing their distribution in distance or redshift and their intensity or absolute magnitude space, two key properties of any astronomical objects, right? So in this problem, we might, the challenges include things like how to handle the evolution with redshift, how the distribution's changing with redshift. I certainly don't want to assume they're independent, even though those kinds of assumptions were made a long time ago. How to handle this irregular truncation boundary. And finally, if I actually have photometric redshifts, how am I going to handle the errors in those redshifts? And again, standard statistical research, when they talk about estimating distributions like this with errors on the observations, they think about the simplest situations, things like constant variance, everything is Gaussian, right? And then you can do some things. But doing it under these very complex error distributions we just saw is very challenging. So I had a paper many years ago where I took a semi-parametric approach to attacking this. So I modeled the log of this joint density as being a sum of a function of redshift, a function of absolute magnitude, and then a parametric component, a fairly simple parametric component, to kind of like get a first degree dependence between them. So in this model, F and G are both estimated non-parametrically. So when I say that, I just mean no assumed form is taken. We're just letting the data speak for itself. So the idea here is that you want to fit something with sufficient structure, but also give it a good amount of flexibility. We want the data to be able to tell us what is there, right? We don't want to impose our own assumptions any more than is necessary on the form of the model. Right? So this sort of approach, could handle or could address this truncation issue I think it could handle that pretty well. Okay, another example, the so-called initial mass function, stellar initial mass function, the distribution of star masses after a star formation event. So we had a paper back in 2019 where we created a more flexible model for the initial mass function using some ideas from what's called preferential attachment. So creating what I would call a more non-parametric approach as opposed to more parametric power law assumptions that have been made as to how the different stars would be formed in this process. That, to me, again, is an example of a canonical parameter, the estimation of this initial mass function. Other examples include power spectra, like if you're familiar with the cosmic microwave background radiation, people often talk about the power spectrum of the CMB, correlation functions, which we deal with quite a bit, like in weak lensing studies. Those, again, are not often the ultimate target of inference, but they are in some way a summary of this massive amount of data that's available. And in all, again, kind of repeating myself here, but in all cases, we need these as summaries. We want to minimize the assumptions that we put into them. Let the data speak for itself. And that is where we have really advocated for the use of non-parametric and semi-parametric approaches to doing this estimation. And again, it's crucial to understand uncertainty. We need to put error bars, meaningful error bars on all these quantities that can be propagated forward into the next step. Okay, so that wraps up the second step of inference. These canonical parameters are, in some sense, the crucial summaries of the data, and they must be estimated in rigorous and flexible ways. Michael?
Imagine if you had infinite computing power. Would you prefer to skip the canonical parameters and go straight to inference of the cosmological parameters? Or do you think that the canonical parameters give you some kind of insight into your data that's a crucial step you'd always want to?
I mean, certainly these parameters themselves are of very general interest. I mean, it's sort of like the way in which people discuss results, right? You look at power spectra, you look at luminosity functions. So I don't want to diminish their importance in that sense. So I still think people would be very interested in estimating them and looking at them. But I do feel like in a lot of cases they are sort of an intermediate point to getting to the parameters that you're ultimately interested in. So I think even with infinite computing power, you would definitely be interested in looking at these things. Yeah. Okay, thank you. So again, now we're going to take this last step into the so-called cosmological parameters. So these are physical constants which characterize the universe. And this is where the physical theory really plays a huge role. Understanding the relationship between these parameters and what we can actually observe. This is where the simulation models that I was mentioning earlier come in. One characteristic we see and one source of a lot of challenges, especially at Rubin scales, is multiple data sources can be used to constrain the same parameters. And of course, to get the tightest constraints possible, we want to take advantage of that. But doing a joint analysis over multiple different data sets, which are quite different in character, and I can't assume that they're independent of each other, doing that sort of joint analysis is very challenging. And just remembering that we just talked about the data at this point are, in some sense, the estimates of those canonical parameters we were just talking about. That's what is going to be used as the input here in a lot of problems. So examples of cosmological parameters, things such as the density of baryonic matter relative to the critical density, the current rate of expansion of the universe, the so-called Hubble parameter, the optical depth. These are some of the simplest parameters that make up the so-called lambda CDM model. When I started doing this 25 years ago, I was actually quite surprised the extent to which questions about the universe had been boiled down to the estimation of a handful of parameters, of real valued parameters, a lot of them. That's an oversimplification of the situation, but it is often the case that there are these physical constants that they're interested in estimating. So to create another example here, I want to talk about supernova for a minute. Supernova result from type 1a supernova result from the demise of a white dwarf. For cosmological reasons, they're important because they are standard candles. At the source, they are of equal magnitude. So by looking at their variability from our perspective, that's telling us something about what's happening between the source and us. That tells us something about dark energy, among other things. So theories regarding dark energy predicts relationship between the redshift of the object, of this supernova, and also the so-called distance modulus, which again is sort of a difference in distances, as the name implies. And this difference, without getting into any details, not that I really could, but this difference says something about the dark energy between us and that object. So it's very critical for constraining parameters related to dark energy. So again, going back to 2007, Reese publishes this critical sample of 182 type 1a supernova. And again, remember, Rubin's looking at maybe 10 million of these or so. This is the sort of relationship that I'm talking about. A distance modulus on the y-axis, redshift on the x-axis. Under a quite simple model, simple parametric model, when the Hubble parameter is 72.76 and omega matter is 0.341, this is the prediction for that relationship. So this is what I want you to imagine, that I take my data, I summarize it in this form, this relationship between distance modulus and redshift, sort of a canonical parameter, if you will. And then under different theories, different parameter values, I get different proposals or different theories for what this relationship should be. So this is, a simple way of thinking about estimating these parameters. So actually, this is some work that I did. We developed methodology for constructing confidence regions for the cosmological parameters. And what I'm comparing here is the blue, the outer band. This is a 95% confidence band on this relationship, just using some very simplistic statistical assumptions, just using basic chi-squared results. But in our case, what we ask the question of is, if I know that it's ultimately the parameters that I'm interested in constraining, I should be able to use that information to get tighter constraints on this relationship, and hence tighter constraints on the parameters themselves, right? The model, the assumed parametric form, is constraining the space of models in a meaningful way that I want to take advantage of. I don't want to lose power trying to protect against theories, against alternatives that I know are physically impossible. So again, this idea of using the physics of the situation. So by using this method, you can get tighter constraints on this relationship, but more importantly, you can get tighter constraints on the parameters. So here we're seeing the confidence region in the actual parameter space. So our approach, this MES approach, is this is a 95% confidence region on the parameters. And just to be clear, this is a frequentist approach. It is not Bayesian. I know that Bayesian methods abound in astronomy and cosmology, and I don't, that's great. But we wanted to develop a frequentist approach to this. This is actually a 95% confidence region for this pair of parameters. But that is still kind of a simplistic approach for modern data, because it's all based on having a likelihood function. Likelihood-based approaches are becoming increasingly difficult at the data volumes that we have now. And this is getting back to this variance-based versus bias-dominated challenges of inference, right? With more and more data, any assumed likelihood form, any assumed likelihood function can be shown to be invalid and potentially leading to significant bias on your ultimate results. So what we've seen is a dramatic increase in the interest in so-called simulation-based inference. So again, what would you do in a situation where your best understanding between the relationship between the parameters and the observables was from a simulation model? So I can't actually write out a likelihood function and assume that all these things are Gaussian or they have an exponential distribution or anything like that. I don't want to assume that things are independent. I want to be able to incorporate things like contamination, different measurement error distributions. I want to get all these features included, because if I don't, the bias is going to overwhelm any results that I get. It's going to introduce significant errors in my results. So back in 2013, we had a paper where we used so-called approximate Bayesian computation, which I would consider like the original approaches, one of the original simulation-based inference approaches. It's a fairly simplistic approach, but it does provide a useful starting point. We took this approach for the same problem, this supernova parameter estimation problem. And again, part of the value there was that you could incorporate in the measurement errors in that process, because all you're thinking about is forward simulating the data, right? You start with your cosmological parameters, you propose particular values for the parameters, and then you forward simulate the process to get your observed data, or a model, a simulated version of your observed data, and then you can compare the simulation with your actual observed. So if you do an adequate job of modeling that forward process, you can capture all of these intervening, contaminating, and error-filled processes. You're actually comparing like versus like in the end. So you imagine doing this all over the parameter space, simulating data sets for all different parameter values, and then only accepting those candidates for which the observed and the simulated data are sufficiently close to one another. That's the basic idea behind ABC, right? You move around the parameter space, you're actually sampling from the prior. You move around that space, you simulate data under each of those theories, and you compare with your observation, only accepting those where they're sufficiently close. You can prove that under some assumptions that the accepted sample will be a draw from the posterior in that case. So that's what I'm showing here. And again, now I've switched to a Bayesian approach just to show that I'm quite flexible. And honestly, I think most statisticians are these days. They're quite pragmatic in the methodology they use. But yeah, so this would be an approximation to the credible region, the 95% and 68% credible regions over these two parameters using an ABC approach. Now, I'm brushing over a lot of computational details, as you probably can imagine. There's a lot of sophisticated algorithms that kind of make it more efficient than what I just described. But fundamentally, that's what it is. You move around the parameter space and you accept only those that give you simulated data sets that are close to what you've actually observed. These kinds of techniques are, again, getting used more and more. Now the focus is more on what we would consider machine learning-based approaches. One that I will highlight is the so-called neural posterior estimation. And you can see it actually has similar sort of flavor. I assume that I have a parameter space with a prior on it, and I can draw from that prior, and then along with that draw, I can simulate a corresponding data set, which again incorporates all of the contamination and all the other observational effects I want to model. I generate a bunch of those. From that, I now use a neural network on this training set to learn the relationship between the data, between the x and the parameter, the posterior on that parameter theta, right? So normalizing flows are very popular for this step. That's a very common technique at this point. So you're actually going to learn a distribution. So in this network, the input is going to be the data. The output is actually a distribution on the parameter space, the posterior. So I train that model using that training set I've constructed, and then I take my actual observed data, plug it in, and I get my posterior out of that. And here, I'm showing here a figure that I pulled out of a paper where they used this sort of approach for estimating parameters associated with exoplanet atmospheres. And I've actually been talking to Peter about similar types of problems during my time here. So you can see that in the end, you have the data here, the spectrum, that's being plugged in to obtain the posterior on a pair of parameters in this corner plot, if you will, in the lower right of this plot. You see more and more uses of these kinds of approaches now. It's a very active area of research in general, but I would argue specifically in cosmology, that cosmology is really pushing the boundaries of what these sorts of methods are able to handle, and it really presents some of the most challenging problems for these sorts of methods. Okay, so the point here was that the ultimate goal is often the estimation of these cosmological parameters, and the challenging aspect is often the complexity of the relationships between these parameters and what we can actually observe. So thinking in terms of simulation-based approaches, that's going to be crucial moving forward. All right, so this is just a summary of the main points that I've been making during the talk. But I really want to stress that I think that moving into the so-called Rubin era, as we could call it, there's a range of very challenging statistical problems. I've tried to touch on a lot of different problems here. If anyone is interested in getting further into any of them, I'm happy to discuss. But to the students here, I know there's a lot of students in the room. I really want to emphasize that, if you're looking to go to grad school in statistics, machine learning, whatever, there is a lot of room for research in this space. So I hope that I've at least given you a taste of what it's like to work in this field. All right, and again, you can reach me. This is my email address. We have a group at CMU which is specifically working on statistical methods in the physical sciences, the so-called STAMPS group. You should look us up. You can sign up. We have regular webinars that you might find interesting if you're interested in getting more detail on these sorts of problems. I'm also part of the McWilliams Center for Cosmology at CMU, which is heavily involved in these sorts of problems. And finally, I'll put in a plug for the so-called Informatics and Statistics Science Collaboration of the Rubin Observatory. I was the co-chair of it for about 6 years. This is one of 8 science collaborations within the Rubin Observatory. These are the groups that are actually charged to do the science with the data. And I'm happy to say that they had the foresight to create one of these that is specifically targeted towards addressing statistical issues. On some level, almost every problem that Rubin faces is a data science problem. It's all about data, and I mean, there's a lot of engineering problems, of course, but getting the science out, it's a lot of statistics. But we try to play a role in advancing the level of the methods that are used in that space. All right, thank you. Thanks a lot.
Does anybody in the room have questions?